Let us start lecture 58. The course is on phase diagrams in single component and binary systems. The topic what we will cover today is on the evolution of phase diagrams with different values of enthalpy of mixing of solid and liquid solutions. In fact, we have been discussing on the same topic for the last couple of lectures. In fact, last class what we have talked is about evolution of Eutectic phase diagram, okay. And we have taken 4 major combinations, and we have also talked about different sub combinations. And we have seen in combination 1, which talks about the ideal solid solution and ideal liquid solution, and we got isomorphous. Combination 2, where we have taken del H mix for the liquid solution to be highly negative, but the solid solution of del H mix of solid solution is considered to be 0, that means ideal. And we have seen that there are 2 I formation in the phase diagram and the liquid stability goes up, okay. And we can get liquid below the melting point of the lowest melting point of the metal, which has a lower melting point as compared to the other element, okay, for the binary system. And the third combination we have seen that when del H mix solid is highly negative, whereas del H mix for liquid is highly is considered to be 0, that is ideal. We have seen the solid stability goes up. We still will form 2 I, and those 2 I's will meet at one point, and that point will exist at a temperature which is above the melting point or an element which has a higher melting point compared to A B couple. Okay. Now, that time we see that solid stability goes up, and finally, we have taken a combination where del H mix for solid is positive and del H mix liquid is negative, and we see that with the variation of that combination, we see an evolution of eutectic phase diagram. In fact, if I try to look at what we have done, just a kind of summarizing what we have done till now, is we have taken combination, we have taken definitely a regular solution approach, regular solution model. T and P are considered to be constant, P is 1 atmosphere, and with T there is a difference. So, each T, when we keep our temperature fixed, that time we try to see the equilibrium with the help of free energy composition diagram for a binary system. And here we have taken a binary system where A and B are 2 pure metals, and X A and X B as the mole fraction of A and B, and when we add them together we get 1 mole of solution. So, on that basis we have developed our free energy for liquid solution as well as solid solution, and we have gone ahead with the understanding of equilibrium condition at each temperature, pressure keeping constant at 1 atmosphere. So, combination 1 is the simplest one, where del H mix for both solid and liquid are considered to be 0. It yields me a phase diagram. This is T M B, this is T M A, and A B are the 2 metals. This is X B equal to 1, X B equal to 0, and X B is varying this way. So, we get a phase diagram like this, we get an isomorphous, where this is liquid, this is solid, and here solid plus liquid. So, isomorphous phase diagram. We have seen how this diagram evolves. Now, combination 2, we got del H mix solid to be 0 and del H mix liquid to be less than 0. So, that time we got a phase diagram like this. This is liquid, this particular field is S1 plus liquid, this particular field is S2 plus liquid. We have a lowest point which is below melting point of A also, and this is solid side. Okay. That is the phase diagram we get. Now, combination 3, we got this, and that time we got a phase diagram like this. We got a phase diagram like this, above which we have liquid, here solid, here S1 plus liquid, and this field S2 plus liquid. Okay. And we see that there is a maximum point which is a single point, and that single point, as if that if we take that composition down, let us say this is x0 composition with respect to B. Now, that composition as if it is acting like a pure metal. Okay. So, this is acting like pure metal. So, that means the melting point is basically one single point, one single melting point, even though it is having a presence of both A and B. For example, if we talk about melting point of pure B, they are melting at a particular point, that means at a particular temperature. Same is happening over this point, where though it is a mixture of A and B, but still it melts at a particular temperature. Okay. So, that particular point we can name it as congruent melting. Okay. So, that means the solid stability goes up. Similarly, here also if you see, this is acting like a if you consider this is to be x0, this is also single, this is also acting like pure metal, fine, and this corresponds to a composition x0 which is a mixture of A and B, though this is not a pure metal, but still acts like a pure metal because one single point it is melting. Now, this point will actually get to a eutectic point later on if I consider the combination 4. So, now in the combination 4, we have seen delta H mix for solid is greater than 0 and delta H mix liquid is less than 0. So, that kind of combination, one another combination was this value is greater than 0. So, or we can say other way around, the difference between these two del H mixes, if that difference is very large, okay, and I would say large negative, if I try to make a difference between del H mix liquid minus del H mix solid. Okay. So, that time we have a particular pattern, and if del H mix solid is less positive, so then we have another particular pattern. So, then in the case of this case, we get a pattern like this. This is TM A, this is TM B, this is TM A, x B equal to 1 and here x b equal to 0, x b is varying this way. So, we have said that this is S1 S2, this is also S1 plus liquid, this one is S2 plus liquid. Okay. So, and this particular gap is coming when it comes when the del H mix is positive, and this indicates miscibility gap. Miscibility gap. So, that means this means that we have a possibility of phase separation. And when I talk about this combination, so we have talked about this one. Now, if I talk about this combination, then it yields me a particular phase diagram which is typical eutectic phase diagram. So, this is x b varying this way, x b equal to 1, x b equal to 0. Remember, y axis is temperature, and this is T m b, this is T m a, and the phase diagram look like this. If I phase diagram look like this. So, here where this is liquid, this is S1, this is S2, this is S1 plus liquid, this is liquid plus S2, and here couple of lines we have to consider. These two are this one and this one, we can call it as liquidus. In fact, this all those lines are liquidus line. Why? Because this line indicates an equilibrium between solid and liquid. That line would be if for the liquid composition, that line would be liquidus line. Here also these two line would be liquidus line, and similarly these two line are liquidus. This one is liquidus. Okay. So, here this and this are liquidus, like that. Now, in fact, we have a solidus line. This is solidus. Solidus line is indicative of the composition of solid which is in equilibrium with liquid. Okay. Here also we can say that these two lines are solidus. These two line solidus, and in fact, here also this line and this line are solidus. Okay. So, here we get liquidus, this line which indicates the solid 2 composition which is in equilibrium with liquid. This is solidus, this is also solidus, and we have one line. This line is basically indicative of eutectic line. So, we have two lines. This line we call it solvers, this line we call it solvers. In fact, solvers lines are those which are composition of solid, and that composition is in equilibrium with another solid. So, that those will be solvers. In fact, solvers line becomes very critical in case of precipitation hardening alloys. For example, aluminum copper, which is 2000 series main alloying elements, aluminum copper. So, that time we have also a solvers on the aluminum side, and that solvers allows us to get different precipitates, starting with GP zones, theta double prime, theta prime, and finally theta, which is the equilibrium precipitate phase. So, that way we can improve its mechanical property. So, these are the important lines, and we have one point which is this point, which is acting like a pure metal. See, if I take any composition exactly matching with this composition, we can get, this is x0 let us say, that composition will melt, will solidify if I start with a liquid phase just like a solid pure metal when pure metal gets solidified. So, that is an unique point and that point is called eutectic point. In fact, at eutectic point, the eutectic point is actually, we have to consider two things together. One is eutectic temperature, which is called Te, and eutectic composition, which you can call it as Xe. Instead of X naught, I can put it Xe, just to indicate eutectic temperature and composition. That is an unique composition. No other point can have in this entire phase diagram where the similar situation can have. And why this is unique? Because at this point one liquid actually breaks into two solid S1 plus S2, okay, at this particular temperature and composition, and this is under equilibrium. We have seen before also with the help of composition, free energy composition diagram, composition when once we reach to that particular temperature, we have a kind of situation that common tangent will pass through all liquid phase as well as both solid 1 and solid 2 curves at particular unique points, and that gives us this particular reaction which is under equilibrium. Fine. So, this is typical of, this is called eutectic reaction. Eutectic reaction. Fine. So, we will try to learn more about this eutectic thing, but at least one thing it is very clear that as we increase the temperature, as we increase the positiveness of del H mixed solid, what happens, this line is actually gradually moves upward. In fact, if we parallelly, if we try to see the difference between these two del H mix values of liquid and solid, taking the difference is basically del H mix liquid minus del H mix solid, then as we increase the difference, relatively this one also shift towards downward, this one also shift downwards. Fine. So, like that it will shift like this and we get a particular point like this. In fact, you see you are actually getting eutectic phase diagram because of the relative movement of both liquidus, solidus, solvus lines, and we get a eutectic phase diagram. It happens because they relatively they come closer to each other, those liquidus solidus line as well as liquidus line and solvus lines, because here this is nothing but solvus, this is also solvus, and other liquidus and solidus you can see that they are coming closer to each other as we increase the difference between del H mix Al minus del H mix solid. This difference goes up, this it will yield to eutectic phase diagram. Fine. Now, if I increase this difference further, okay, let us have a situation we increase that difference further. So, what will be the situation? So, now we can have two more situation like that. Let me go to the next page. I am increasing the difference between these two values, L minus solid, this difference goes up and del H mix solid is greater than 0 and del H mix liquid is less than 0. So, this difference is actually going up. Fine. So, what will be the change in the phase diagram? So, we will see a change like this. If let us say this difference is del H mix, del H mix dip, D means difference let us say, and this will be always negative. You see this is negative and this is positive. So, there is a negative sign, this will be negative. Now, if I have that, you will see a situation like this. Let us say I will just put some arbitrary value, then you would understand. X b equal to 1, x b equal to 0. Let us say this is T m b, this is T m a. Let us say del H mix is solid equal to let us say plus 15 kilojoule per mole, whereas del H mix liquid is minus 20 kilojoule per mole. Under this circumstance, what could be the situation? The situation would be like this. Fine. Since this is very large, the terminal solid solution, in fact, let me just tell you, in this particular phase diagram, eutectic phase diagram, one particular zone is to be understood. These S2 and S1, this S2 and S1, they are called terminal solid solution. Why terminal? Because they are appearing at both pure metal sites. That is what those are called, terminal solid solution. Now, if I try to look at this particular situation, where I see that this high positive values of this would actually allow a very strong possibility of having similar kind of atom pairs, and that actually allows this particular terminal zone to get shrunk, and this one is highly negative. So, liquid stability would be very high. So, this particular point will go down heavily. Okay. Now, condition 2, if I see, let us say del H mix still remains 15 kilojoule per mole, whereas del H mix liquid, let us say it becomes minus 10 kilojoule per mole. So, that case you see that this particular difference is actually decreasing. So, here the stability, phase separation ability remains same in case of solid, but since the liquid stability has decreased compared to case 1, this is case 2. So, this particular point will shift upward. So, liquid stability will go down. So, if I try to see the phase diagram, let us say this is temperature, this is T m A, this is T m B, this point will shift upward. Okay. We have eutectic, definitely. Here also we have eutectic, but this terminal solid solution zone will expand. Okay. This is liquid, this is S1 plus liquid, this is liquid plus S2, this is liquid, and this zone is S1 plus S2. So, this is S2 and this particular small zone is S1. Now, here this is S2, this is S1, S1 plus S2, liquid plus S2, S1 plus liquid, like that. So, what changes we have noticed? Since liquid stability has actually decreased, this point has moved upward, that allows this particular line to expand a bit. Okay. So, that is what exactly happened, and that allows the extension of S1 and S2 zone, single phase terminal solid solution zone. And now, if I third case, let us say I maintain del H mix solid to be equal to 15 kilojoule per mole and del H mix liquid, let us say minus 5 kilojoule per mole, that time the change what we will notice is, if I try to plot it side by side here. So, this is the case third, this is x p equal to 1, x p equal to 0, x p equal to 1, x p equal to 0, x b is varying this way, this is temperature, let us say this is T m A, this is T m B. Now, I will see that this point will further move upward when we go to third case. This is the case 3. So, I will see that this will further move we have eutectic and this zone will go up. Okay. So, this is the kind of change, rest you just put it. Okay. This is S1 plus liquid, this is liquid plus S2, like that way these changes will be noticed, fine. Okay. So, this is one kind of subsets or sub combinations what we can consider within combination, main combination 4. Now, let us actually get into the eutectic phase diagram and try to understand few more things. In fact, we can understand some of the tricky phase transformations what is done, and thermodynamic basis for that phase diagram also can be understood. Of course, kinetic part we cannot realize here, because it only talks about free energy, it does not talk about time, but still we can get an idea why that transformation happens in that fashion, fine. So, in order to do that, so now let us analyze eutectic phase diagram or analysis of now we have eutectic phase diagram. Let me draw this eutectic phase diagram on the right. X p is varying this way, x p equal to 1, x p equal to 0, temperature is this. Now, this is T m B, this is T m A, and please understand that all throughout our course we have taken the element B has the higher melting point and element A has lower melting point, and that is followed uniformly over the entire lecture series. So, now these 2 points, if I draw it in a simple fashion without putting any curve. So, let us say this is my eutectic point. Okay. This is a typical eutectic where we have terminal solid solutions and we have one eutectic point. Now, let me draw at this temperature here and here. This 3 temperature, let me draw composition free energy diagram again. So, this is T1, this is TE and this is T2. Now, if I draw at T1, remember the reference melting point free energy for pure metal will be same as before. And we are taking one temperature which is this is one temperature we have chosen, this is another temperature, this is this is TE, this is T1 and this is T2. These 3 temperatures will be having our free energy composition diagram. Now, first let me draw it at T1 0 0 You please follow it up. It is considered the most stable phase is that particular pure metal free energy is taken as 0. Now, corresponding if it is a T1, corresponding liquid line is here, liquid free energy of pure B is here, and in this case it is here. Okay. And this is G1 of liquid, this is G1 of solid, this line. Now, if I draw this at T1, this is G2 of liquid, and the solid line would be this. This is G2 of solid, and this one is G2 of liquid. Okay. Now, we see that one tangent is lying here, another tangent is lying. Now, these two compositions, if I this is one composition which is XB. Now, we will try to follow it up this style, follow this style S1 composition of phase S1 in equilibrium with liquid, and this one is composition of in terms of B. So, XB is varying this way, this is G, XB equal to 1, XB equal to 0, two pure metal sites. This is XB of liquid in equilibrium with S1. The composition, this composition is XB of liquid in equilibrium with S2, and this one is XB of solid 2 in equilibrium with liquid. These four compositions. So, these four compositions, let us put it here. One composition is this one, these are the four composition. We can mention that XB of solid 1 in equilibrium with liquid, XB of liquid in equilibrium with solid, XB of liquid in equilibrium with solid 2, and this one is XB of solid 2 composition in equilibrium with liquid. Fine. All those points we have marked. But can we have some other common tangent? Okay. Yes, I can have a common tangent if temperature is T1, and we can see that one common tangent I can actually consider. That common tangent, let me do it with a different color so that it can be understood properly. If I deal with the red ink, so that common tangent will be passing through this. So, now here I have composition this one and this one, which is XB of S2 in S1, composition of S1 phase in equilibrium with S2, and this one is XB composition of S2 in equilibrium with S1. Now, we can actually mark those two compositions. Those two compositions are coming, XB S1 S2 is coming right to XB S1L, and XB S2 S1 is coming on the left of XB S2L. So, one point is at this location, another point is at this location, and these two compositions are XB S2 S1 in equilibrium with S2, and this one is composition of phase S2 in equilibrium with S1. Okay. This is please mark those points, then only it will be clear. Okay. But let us see that tangent, this red color tangent, this tangent is actually above the tangent of tangent. If I consider these two composition range, these two compositions, the tangent is above the brown tangent what we have drawn. So, that means that brown tangent compositions will be stable compositions and the red tangent to corresponding equilibrium compositions will be metastable compositions. Okay. So, that means these 2 points are metastable points and all other point marked with a brown one are actually stable compositions. Now, if I try to look at temperature T2, what will be the situation? So, if I draw the same diagram at T2, this will be definitely G1S 00, GB naught S, GA naught S, and this will widen a bit. This is GB naught liquid, this is GB naught, GA naught liquid. Why that gap will widen? Because if I go to T2 temperature, you see the gap between these two liquid and solid free energy lines are increasing as compared to T1. Now, this point would be, this will be G1 of liquid and this will be, and now let us draw the free energies of solid solution and liquid solutions. So, this is G2 of solid and G2 of liquid would be, let us say this is G2 of liquid. Okay. In here also this was G2 of liquid, the green one. Now, if I try to see common tangent, the common tangent, the red color one is between solid 1 and solid 2. This is XB solid 1 in equilibrium with solid 2. This is XB solid 2 in equilibrium with solid 1. And remember, we are drawing it at temperature T2. And XB is varying this way. XB is varying this way. This is XB equal to 1, XB equal to 0. Fine. So, these two compositions are marked here. So, now here these two are stable compositions. Why? Because that is the minimum tangent, the tangent, common tangent is having the minimum energy over with respect to all other free energies. But can I consider any other tangents which will pass through 2 points on 2 different curves? So, one tangent can be drawn like this. One tangent is drawn here, another tangent can be drawn here. Okay. So, these 2 tangents, if I could draw a common tangent, that indicates equilibrium, but that tangent, if you see, this brown tangent is actually above between those 2 composition points, above, or those 2 compositions which are in equilibrium with respect to brown tangent, they are above the red color compositions, which are stable compositions. Now, let me mark those compositions. So, this is one composition, this is XB of composition liquid, this is solid 1, because towards air each side, solid 1 in equilibrium with liquid. We have one more composition there, which is Xb composition of liquid in equilibrium with S2. Here is one more point which is actually composition which is with in equilibrium with the solid composition. This is composition of liquid in equilibrium with solid 1. Here we have one more composition which is Xb of solid 2 in equilibrium with liquid. Now, let us see and these compositions are actually above the red line common tangent. So, that means those are all metastable compositions. Those are equilibrium composition because they are falling on common tangent, but since they are above the red color, the stable common tangent compositions, they will be all metastable compositions. So, what are those points? Can we mark it over T2 line? So, now if I try to see this one, this one is coming, this was basically equilibrium between solid 1 and liquid. So, equilibrium between solid 1 and liquid is falling on the right side of this particular composition. So, it is coming here. Now, if I try to do this particular one which is coming left to this place, this particular composition, and if I try to look at so this composition is here, this is Xb S1 liquid, this is Xb S2 liquid. Okay. We can actually mark other two compositions which are in equilibrium. This one is Xb liquid of S2 and this one is Xb liquid in equilibrium with S1. Okay. These interesting situations now. All these compositions are basically metastable compositions. At T1 the red circle was metastable and at T2 the greenish color or kind of this particular color, that circle is indicative of metastable compositions. Fine. Now, let us see what is this particular composition. Okay. This is the equilibrium between solid 1 and solid 2. Now, if I try to move from T2 to T1 and if I extend this line if I extend, okay, so this extension should pass through this. This extension is nothing but the equilibrium between solid 1 and solid 2, there is two solvers lines. Okay. And here also this is the same one as S2 compositions, two solvers. Now, if I try to drag this line if I drag, it will go through this, since this is the solidus line and that solidus line is about the composition of solid 1 in equilibrium with liquid. So, this is also solid 1 composition of solid 1 in equilibrium with liquid. So, it should fall on that line. Similarly, same logic if we follow it up, it will all be like this. Okay. Now, interestingly, I can actually have those metastable composition existing on the phase diagram, but how do we differentiate between metastable compositions and stable compositions? So, that question we need to respond, and that response comes when we put that metastable compositions in terms of a dotted line. If you recall, in case of single component system, we actually extended that stable equilibrium line into another phase with the help of a dotted line. So, whenever here also, since those compositions are metastable compositions, as we have marked those compositions above the stable composition falling on the common tangent. So, those compositions can be shown with a dotted lines in eutectic phase diagram also. So, now if I try to this particular plot, if I redraw it, the redraw would be like this. This is T m B, this is T m A, we have this point, Okay. Now we can put this one as dotted like this one as dotted like this one dotted like this one, and this one. So, these dotted lines are corresponding to metastable compositions, and these are also found out from via that common tangent rule. Okay. So, this is temperature and this is composition. Now, if I try to do it at T equal to T equal to T e, the only thing would be this particular 1 0 0 T equal to T e, G is varying this way, x p is varying this way, x p equal to 1, x b equal to 0. This one would be G 1 S, this one is G b naught liquid, G b naught solid, G a naught solid, G a naught liquid, G 1 liquid. Now, the diagram would be I am just drawing it with schematic representation. There will be a common tangent and that common tangent will pass through these three compositions. So, these are x p of S 1 in equilibrium with liquid and S 2. This one would be x b of liquid in equilibrium S 1, equilibrium with S 1 and S 2, and this composition is x p of S 2 in equilibrium with liquid and S 1. All three phases will be in equilibrium and those compositions are marked, those are stable composition. These are three compositions. This is x b S 1 in equilibrium with liquid and S 2. This is x p liquid in equilibrium with S 1 S 2, and this is x p of solid 2 in equilibrium with liquid and S 1. Okay. Like that way we get the entire information about the metastability as well as stable situations in this eutectic phase diagram. And here I need to mark that this is liquid, this is solid 1, this is solid 2, solid 1 plus solid 2, and here solid 1 plus liquid, and here liquid plus solid 2. Okay. So, these information we are getting, we can actually reflect those metastable compositions on phase diagram, stable phase diagram, okay, by dotted line. Now, let us see one interesting part. In this phase diagram, we have one unique point, two unique point rather, which are actually having same G 2. Okay. G 2 of liquid is equal to G 2 of solid. One point is coming at this location where free energy of G 2 is crossing the free energy of liquid, and another point is coming here. Okay. Here also I am getting those 2 points. Here also I am getting those 2 points. Okay. Now, interestingly, these points can also be reflected over eutectic phase diagram. You see these 2 points, are lying between the equilibrium composition of solid 1 in equilibrium with liquid, liquid in equilibrium with solid 1. Similarly, composition of liquid in equilibrium with solid 2 and composition of solid 2 in equilibrium with liquid. So, those 2 points are lying between these 2 compositions. So, that means it is lying in between this one and this one, this one and this one. Okay. So, now if I try to plot those points here, so these are the temperatures we have considered. This one in temperature, this was another temperature we have considered. Let us put those points. So, now this point is appearing here, this is appearing here. Similarly, it is appearing at this location and at this location, and in case of T e, if I do it over T e, this is T 1, this is T 2, T it is lying here at this location and this is at this location. And if we follow it up with those points and then keep connecting, you will see that connection will actually pass through like this. Here also it will pass through like this, okay. And then they will cut, and this cut is coming below eutectic temperature, fine. So, now interestingly you see that if I see here these 2 points, between these 2 points I see that liquid is actually existing in both stable as well as metastable mode, fine. For example, let us take this particular thing. Here between these 2 points I see the liquid is actually below the solid free energy line, but it is above the common tangent line. So, that means that liquid would be definitely metastable. So, here below eutectic, the temperature, any temperature you consider, those will be, that liquid would be, here we have a liquid existence, but this liquid would be metastable, fine. Here also between these two we have eutectic temperature. Here I see between these two, these actually these 2 points are actually staying above the common tangent. So, that will be also metastable. So, this liquid is also metastable. Now, if I try to do it between these two, I see here we have stable liquid, but if I try to see this region and this region, that time let us see what is happening at T 1. This is at T 1 between this and this zone. Okay. I see the liquid free energy is actually higher than the common tangent, that brown tangent, and on the left side also between these two composition we have liquid free energy is higher than the common tangent. So, the liquid will be metastable between those two region, but stable between these two region. This region liquid would be stable because liquid has the lowest free energy, but between these two we have metastable liquid. Like that way we can actually decide which liquid is stable, which liquid is metastable. Now, this particular locus point is actually called T naught point, T naught line. Here also, and you can say this is T naught for S2 and this one is T naught for S1, and these two dotted lines actually indicate one interesting, it can actually explain one interesting phase transformation. So, in phase transformation we have a kind of phase transformation called these dotted lines, the T naught lines, it actually can explain one interesting phenomena in material science, which is called glass formation. Glass formation. We could see even below T e the liquid remains stable, but in its metastable condition. Okay. So, below T equal to T e, liquid still remains metastable. So, that means liquid existence is still there, but though metastable, but still there. Now, let us say I take any composition between these two lines, between these 2 points, any composition if I take, okay, at T 2 between those T naught locus points, any composition I will take, that particular liquid if I cool it fast, if I do not allow any time for segregation to occur, so they can remain liquid even below eutectic temperature, and as we cool down a liquid, now the liquid viscosity goes up, and that viscosity increment follows nearly Arrhenius equation. So, that means viscosity increment can happen exponentially, okay? And when the viscosity of the liquid goes around 10 to the power 14 Pascal second, that liquid becomes so viscous that the shear movement of atoms does not happen easily, and that can be considered as a solid. Okay? So, liquid becomes a solid. So, that means we have frozen a liquid in the form of solid without changing its structure. Okay? And liquid structure is nearly random, and that structure, if I hold it by forcefully, if I hold it at a lower temperature, and that time it is called a glass. Okay? So, glass formation in polymers or metallic systems are there, and the basic fundamental is lying here in the phase diagram. So, the composition should lie between the T naught points in eutectic compositions, and that will have the chance to go for glass formation. Okay. So, that is what, for example, what I said, a liquid, if I try to cool, and this is the viscosity, if I liquid I try to cool, this is temperature, I cool down from melting point, let us say, and here it is T e. Let us say I have taken a composition equal to eutectic composition. Now, if I cool it, the viscosity will be like this, viscosity change would be like this. So, now let us say this particular point temperature viscosity is 14 Pascal second, and when it reaches that corresponding temperature, we call it T g or glass formation temperature. And that happens due to metastability of liquid below eutectic temperature. So, this glass formation is possible because of this very concept of metastable liquid on eutectic phase diagram. Okay. So, this is one such example. There would be examples like partitionless or partitioning transformation, phase transformations, that will be common when we consider eutectoid also. Okay. We will try to see eutectoid composition. So, when we try to consider eutectoid composition, that time we will explain the partitionless and partitioning transformation with reference to free energy composition diagram, and that would be applicable for both solid and liquid, both eutectic and eutectoid phase diagrams. So, that one we will consider while discussing eutectoid phase diagram in our next lecture. So, let me now stop here. We will continue our discussion on phase diagrams. Now, we will try to draw phase diagrams considering two solids. Till now, we have taken one liquid solutions and one solid solutions, and we got eutectic phase diagram. We will now try to get into a solid phase transformation, and that time we will get a eutectoid phase diagram. And we will also try to look at one more transformation where it will involve liquid solution as well as solid solution, but that time we will consider two solid solutions again, and that time we will get a typical phase diagram called peritectic transformation. Okay. So, we will cover these eutectoid and peritectic, and at the same time we will try to understand partitioning and partitionless transformation with reference to eutectic as well as eutectoid. So, this will be done in our next lecture. Thank you very much.